Okay, so I'm about to start writing a shooter game, and before I really go into the development, I want to have an idea of the performance of my system. So I wrote an application. It is just some bullets bouncing on the edge of the screen, and I measure the frame rate. In this little competition between pygame, love2d, and the logiqub, these are all scripting languages, so interpreters. They are not compiled languages, so no C, C++, C#, Rust, NIM, Pascal, or D, things like this. They are going to be just too fast, so it's impossible to compete with it, so I didn't include them. But maybe I should have, because as we will see at the end of this recording, maybe it's not that important. It still matters, but not as much as I believed at first. So this is the bullet. It's just 16 by 16 pixels, and as you can see, there is a lot of transparent pixels around it, and this is going to slow down the program. So when we check the code, we will see that actually I'm cutting a smaller rectangle of 6 by 6 around the bullet, because otherwise the graphics card is going to draw the transparent pixels and waste a lot of performance. So this is pygame. Pygame only achieves 32 FPS, 38 FPS for only 1000 bullets. Why is it so slow? So pygame is slow because Python is slow. There's nothing you can do about that, or maybe there is, because you can use Cython bindings, which allows Python to go faster by using C data structures. And you can also use JIT compiler like pipewire, but that's pygame, that's how it is, and the performance is terrible. Also, pygame does not use the graphics card very well at all. It's very strange because we are moving to SDL3 now, and pygame was using SDL version 1 at first. It didn't even finish migrating to SDL2, and we already have SDL3. So I was feeling really bad about SDL3 coming while my language is still not done using SDL2. But as we can see, even pygame has terrible performance and still can't use the GPU really well. So that's a good point for me, I guess. So a little bit of backstory. So I first learned about programming at the end of the 90s. We were using Turbo C, and I've seen a little bit of assembler. I don't remember which microcontroller we were programming, but we were also printing circuits and making boards. So I got a good taste of hardware engineering, even though I didn't really want to do that. I didn't care at all, but maybe I should have cared, because at the end of the day, software can only run on hardware, and if you understand the hardware, you can do a much better job at software engineering, but I was young and I didn't know how important that was. Because when you get a device, an electronic device, you cannot like open it and search the internet for the parts and the plan, and you have no idea how the hardware works. And also, for example, the Game Boy was pretty expensive when I was a kid, so I could not like open it and break it apart to see how it worked. And I had no idea what was going on inside of it, so I was not, I guess, educated enough to understand why this part of my career was very important. So I became a Delphi programmer, working with databases mostly. And by that time, it was early 2000. I didn't know anything about C, C++, Linux, and all the C ecosystem. I was just Windows Delphi programmer on databases. That's what I knew. And the only thing I could remember is BIOS interrupts. And at that time in the 2000s, you could not do that on Windows anymore. You had to use system calls and libraries and things like that. So I was trying to relearn how to make games, but I didn't find the answers that I was looking for. And so I tried many frameworks, and problem with frameworks, you cannot understand what's going on behind the framework. So if I try WPF, I cannot look inside the .NET libraries and see what Microsoft is doing. The same thing with XNA, Giteros, etc. The low-level parts, you cannot see them, so when you have a problem or performance or whatever, you don't know where to look and how to improve, and that was frustrating. I was already using Python by 2012, so 3 years later, 2015, I tried Kiwi. Kiwi framework, during that time, was still using some pygame code, and eventually they optimized it and removed the dependency on pygame. I was like a big fan of Kiwi because you could make multi-touch applications and deploy on everything: Windows, Linux, Android, iOS, whatever. However, it was slow. I made the Ludum competition weekend, and the thing was so very slow. Trying to create a shooter game, I told myself I would never use it again. So I began searching why it has to be so slow, because I didn't understand why Python was so terrible at it. So I found about love2d, which is another framework that I tried. And as you can see, we have now 6,000 bullets and 58 FPS. So compared to pygame, we have only 38 for 1,000. It's much better. So what is a virtual machine? In this context, for an interpreter, a programming language interpreter, the virtual machine is an execution context for virtual instructions. So what happens is that during compilation, the interpreter or compiler generates an intermediate representation of the source code, which is often bytecode. And this bytecode must be decoded by the virtual machine into real instructions that the CPU can execute. Decoding bytecode can be slow because you take basically a number for the instruction, then you have to map this number to a real address of native code and execute this native code. And because you have this extra jump, sometimes the branch target predictor cannot do a good enough job to predict where is the next instruction, and is much slower. Native code is just executing in a straight line except when there are branches, but still it's much faster. So instruction dispatch causes a lot more of CPU stalls because you have too many branches basically. But why use bytecode at all? Because bytecode is portable. If you remember, Java mantra is compile once, run everywhere. So basically you compile the application once and you can run it anywhere you have a virtual machine for it. Native code, on the other hand, will not execute. For example, if you compile for x86 with a C program, the same binary will not execute on ARM because the assembly code, the bits, the zeros and ones are completely different. But with a virtual machine, you can have the same opcodes for all the instructions, and then the virtual machine is going to translate them to native instructions and execute the program for you. So that's why bytecode is kind of useful. So what is a JIT compiler? A just-in-time compiler is going to look at the code from the virtual machine, the bytecode, and generate native code on the fly while the program is running. So it's going to detect the odd paths and recompile those odd paths. So this applies to luajit, but also Java, .NET, etc. And this means that just-in-time compiler can sometimes be faster than a C program because it can see the data access patterns and optimize different versions of the same function as the data access pattern changes. So because the JIT compiler can adapt the code to the data that is dealing with, it can be faster than a C program that doesn't know what kind of work it has to do. And at that point, I was studying a little bit the work of Mike Pal, who was a website for luajit, and he's explaining what he has done. And you have a lot of references on the web about what he was doing at this time. You can see like 2015, it was really a big topic during that time. So I didn't read his code or even go in depth into it. If I remember, he was about to do garbage collector and continue working on performance, but eventually I think there was not enough interest and he did not give up on the project. But the author of the Lua language with in a different direction than what Mike Pal was trying to do. So luajit works with Lua 5.1, and today we are at 5.3 or 5.4, and they are not going in the same direction. So from that point of view, I thought, okay, I cannot rely on my pal and Lua to do what I want to do. I better do it myself. So I did do it myself. And compared to 58. So that's like 38% faster than love2d. And that's the work of just myself. I'm pretty happy about it, although it's not really that impressive because I didn't write anything crazy. It's just common sense. The biggest problem with scripting languages that interface with C libraries, which is called the foreign function interface, such as luajit, FFI, and GNI, which is the Java native interface, etc. Is that the data type conversion and the function calls, they are not straightforward. And because of that, the whole point of using a scripting language and a library is to use the flexibility of the scripting language with the performance of the library. But if the bridge between the two is slow and you have to go back and forth between the two, you lose a lot of performance. And basically that's why my logiqub is so fast, because my foreign function interface is just really small and I don't waste time there. Can we go faster? So first of all, I have some error here. I need to fix this. It's not a big deal yet. So perfstat, which is what we see here, this screenshot, can show you details about what the CPU is doing. CPU stalls and branch misses means that the CPU isn't doing work. Basically, the CPU is not working as fast as it could because the target correctly, and then he has to discard whatever he was doing to restart all over again. So when you have branch miss prediction, the pipeline has to be flushed and it's wasting time. And also, every function call requires saving a return address and potentially pushing argument and removing arguments, and function calls also waste time on the CPU side. So with this you can have an idea when you create your own programming language what is going to slow it down. But in this workload, the work is mostly on the GPU side. In fact, the logiqub spent less than a millisecond to update the position of all bullets. So there is nothing we can do on the scripting side to make the program faster. The only thing we could do is to write some OpenGL code to optimize things on the GPU side, but this defeats the purpose of having a scripting language and a graphics library to abstract the problem with dealing with the GPU. So we are not going to do that. And to prove this point, you can see on the left I'm painting 100 bullets and we have max FPS 128 and 100 here, and here we are processing on the right 6000 bullets, but we are painting only 90. Same thing for love2d, and as you can see, the FPS is exactly the same, 102, 102, 128, 131. So moving 6000 bullets is nothing. It's the GPU rendering the 6000 bullets that takes time, and that's the difference with the FPS that we can see in the previous screenshots. So there is no optimization to do except if we want to write GPU code ourselves. So what does this mean? This means for me that you can create a slow programming language and try to speed it up with a just-in-time compiler, which is a very difficult thing to do. Engineering-wise, this is not a trivial problem. Or you can make a fast programming language and you waste some performance when you need more convenience. The logiqub takes the second approach, and we still come out ahead despite it's the work of only one person, and it's much simpler. So for me, it proves that scripting languages to make prototypes for games don't have to be that slow. Like Python, Lua, not a good base. For a beginner, maybe using C or C++, it's just too difficult. Or you try to use a game engine like XNA in the past, which is like monogame today, or you have Godot, or you have Game Maker. But then you also have like Unity, but Unity is proprietary, so maybe you don't want to deal with that, and everything is just too complicated and too slow. So my advice, if you want to learn about game development, maybe learn how programming languages are made and make your own. You will learn so much about what is going on behind the scenes that you will be able to do something like me and be better for such a task than even an engine like love2d, which is well respected, by the way. A lot of developers are using love2d, but even still, when I'm done, given the performance that I can extract from my system, I think it's going to be better in a lot of cases, especially because I will be working on pixel art and 2D stuff, so I fully expect that the logiqub is going to be better than love2d in almost every case. Let's see some of the code now. So this is the Python code. So this is pygame. I wanted to try things with Python here, but this is unnecessary. We don't do that. Here, this is to run the pygame in full screen with double buffering, hardware surface, and no frame. So basically to have it run, or to try to run it in full screen exclusive mode to have the maximum performance, but it cannot do that really well at all. So I don't know what the deal is with this. The performance is bad and it doesn't use a renderer like this is a surface, and this display here. This is not a GPU texture. This is a surface, so it's working with pixels, and this is extremely slow because during the rendering you're doing a flip and pygame expects you to do something like display.update, and then in the update you can put some kind of rectangle that you want to update, so you don't update the whole screen but only a region of the screen, and that's how it's trying to be performant, but it's complete shit for what we are trying to do, which is updating the whole screen. I'll describe the code real quick. So we are loading here the bullet, we're resizing it to the correct dimension and cropping it. We are loading the font to write the FPS, the number of bullets and stuff. This is a logo. I'm doing some transformation because the logo was too big. I resize it. Here is just transformation between degrees and radians. The bullet has an angle and a speed. Here the movement, I update the position, and if it goes out of the screen, then I reverse the angle first, and then I apply a delta to make it bounce, and I do this for every edge. And then there is the main loop, so these are just colors. This is boolean, so when we press Alt F4 to quit, it can quit. You see with running girl false. This is a list of bullets. This is the clock for the FPS, and this is the angle. Basically, there is a cannon in the center of the screen. You can imagine like the center of the screen. There is a cannon, and then it's firing a bullet at an angle, and it's rotating. So this is the angle, and what we do is we increase the angle, and this creates like an animation of shooting bullets on the screen until we reach 1000. So that's what we do. We clear the screen, full black. If we are less than 1000, we add a bullet, and then we increase the angle for the next bullet. And after that, we just move and display every bullet. Then we calculate the FPS. We draw the logo. We draw the FPS text. We draw the number of bullets, and then we print everything on the screen at once. And every program is working like this. We have the same thing for Lua. This is exactly the same code. So you can have a look at it. This is exactly the same code. Also note that love2d has like 3 functions that load, which is the initialization, then the update, where you make things move, and then the draw, where you paint everything. So on that front, I really like the design and the simplicity of love2d. The unfortunate thing is that it's based on Lua, and Lua has this weird thing where they use tables instead of arrays, and also the tables, they start indexing at 1 instead of 0, and the standard Lua library is not as big as Python, so it's doable, but it's not really fun to use, and to interface Lua with C library, it takes a lot of work unless you're using luajit FFI, which makes it a lot easier to interface with C. But yeah, this command here is a limit when I was working to have only 90 bullets. Otherwise, I would iterate over everything, like this, and this, like this. So just some commands depending on what I want to execute. And then we have the logiqub, which has a lot more files and code. Here is the 6000 limits, because I was scripting this like really fast, so it's not as clean as love2d. You have a lot more files, but they are not that complicated. This is the update, which I called paint before. Then you have the paint, which is straightforward, except here there is extra code that is not really needed. Normally it would be like this. You remove this. Alright. That's the hack that I did to limit the loop to 90 bullets instead of the 6000. So we only need this for the paint. This is the scene, this is text box with the bullets, text box for the FPS. Here we have logiqub text, and here we have the logo and a black rectangle to make the text more visible, because when the bullets come into the text, here I have a black rectangle to make it more visible. Otherwise you have bullets everywhere and you cannot read the text. And that's pretty much it. There is nothing else to talk about here. Yeah. Oh, maybe the trigonometry is interesting. So the trigonometry, I can do it like this. So this is just an array of 360 values, one for each degree, and this is a fixed point decimal. So I have a 32-bit integer. The first 16 bits are for the integer part, and the last 16 bits are the fractional part or decimal part. So this is basically the decimal part for all the sinus and cosinus values, and then at the end of it I have the two functions here, and that's how I'm doing sinus and cosinus in this application. So yeah, same thing, resizing the bullet so that it's no longer 16 by 16 but 6 by 6, and the 24 is to rescale it, because 6 pixels by 6 pixels is just way too small. You will not see anything. Well, you will see it, but it will be too small, so I made the bullets from 6 by 6 to 24 by 24, so very easier to see. And that's the end of this demo. And if you have some suggestions for another scripting language that you think is fast enough to compete with the logiqub, just let me know. And that's it.